Hello, and welcome back to Compressible Flow. I'm Professor Steve Miller. Today we'll be turning our attention to a different topic, specifically supersonics in introductory compressible flow. In particular, we'll look at the supersonic flow past wings of finite span. We'll look at and identify regions of two-dimensional flow on these particular wings. And we'll look at how supersonic and subsonic flow will be and occur at the leading and trailing edges of these wings. We might view particular components of the supersonic flow of the velocity, that is, the vector Mach number, as being super or subsonic respectively, which will give us advantages, of course, in our design of aircraft. This will lead to the advantage and analysis of sweep of wings. I'm sure you've been to many airports and seen many aircraft where the wings are swept back, and we'll show the mathematical theory that predicts the advantages that led to swept wings, and of course, its theory. Just like hypersonics and transonics, which we previously discussed, we'll then look at similarity theory for the supersonic wings at hand. Let's get started. First, let's talk about some basic history of the so-called swept wings. We see early swept wings at high speeds were first investigated in Germany as early as 1935, according to our records. We'll see that the swept wings became common on advanced first-generation fighters like the MiG-15 and the F-86 Sabre. These delta wings, which were later incorporated in even newer aircraft, also incorporated the same advantages as swept wings. You might see delta wings like on the famous Concorde or the Eurofighter. The idea of using swept wings to reduce high-speed drag was developed in Germany in 1930 and onward. It was originally discussed publicly at the Volta Conference meeting in 1935 in Italy by Dr. Adolf Bussmann, and we'll look at his history later. Another person named Albert Betz immediately suggested the same effect would be equally useful in the transonic regime, and indeed we discussed this a bit in our transonic class. Indeed, the host of the Volta meeting in 1935 was none other than Arturo Croco, who we discussed previously in our class. He jokingly sketched on the back of a menu Bussmann's airplane of the future, which of course contains the swept wing concepts. And this little figure can still be seen in a scan online. Let's now look at the history of Adolf Bussmann, who I just mentioned, who might be credited as the German inventor of the swept wing. Indeed, he lived from 1901 to 1986. He was born in Germany. Indeed, he was an American immigrant. He joined the team led by Ludwig Prandtl, which also include Theodor von Karman, Max Monk, and Jacob Ackeret, who we've all talked about in this class from a historical perspective. He discovered the benefits of the swept wing, as I just mentioned, and he was involved in Operation Paperclip, which is, of course, the movement of German scientists after World War II to the United States. Of course, he came over with Dr. von Braun in a different group. Bussmann started studies of airflow around delta wings also after his invention of the swept wing. He moved indeed to the United States in 1947 through Paperclip and started work at the NACA Langley Research Center, which is now NASA Langley Research Center, where I used to work. Indeed, Bussmann later became a professor at the University of Colorado and suggested the use of ceramic tiles on the space shuttle, which of course led to ceramic tiles on aerospace vehicles for hypersonic reentry. He did a lot, and now let's look at his concepts of the swept wing and its analysis. Here's one particular example of a swept wing of many, and this is the B-47 on takeoff. It has a rocket-assisted takeoff, and you can see, of course, the wing is not just coming straight out of the fuselage. In fact, a swept wing is described as one that maybe sweeps back as you go in the streamwise direction. So you can see the sweep of the wing from the side of the aircraft. Here's a reverse swept wing. So if you look at the fuselage and the root of the fuselage, you can see the root of the wing to its tip actually goes in the forward direction with respect to the cross-stream direction. That's the cross-stream direction of the flow. In fact, this photo is indeed the Grumman, not the Northrop Grumman, but the Grumman X-29 before the companies merged. This was created to study the aerodynamic stability of the airframe required to use computerized fly-by-wire controls, which was another X-plane. This is a rather unstable configuration for an aircraft, and you can study about this more in other aerospace classes. Let's make some notes about these swept wings and flows before we get started. First, you'll note that with method characteristics, we can find the supersonic flow past two-dimensional infinite span airfoils, just like we used method characteristics to find the flow within a divergent portion of a nozzle. We'll survey particular methodologies to find supersonic flow past the wings of finite span. We'll see that only one analytical method of small perturbations can be used, and we'll have to use a number of assumptions to use this method. First, we'll only be able to examine first-order effects in the fluids, which are important and that the airfoil is very, very thin. Second, we'll have to assume that the viscous effects are negligible, which is difficult because that means we can't account for the boundary layer, which of course exists. And third, we'll have to assume that the flow is irrotational isentropic, of course to use MOC. We'll still find excellent approximations at supersonic speeds relative to actual measured aerodynamic forces. And this allows us to use an analytical method and understand the physics through our equations of motion. This will work wonderfully unless boundary layers separate or the flow exhibits rapid growth. And we'll recall, as we discussed earlier in the supersonics part of the class, way back in shock expansion theory, the regions of influence, where a single perturbation in the flow disturbs everything in, say, a cone downstream of the flow and nothing elsewhere while the flow is supersonic. Let's look at a few images to illustrate these concepts. In this particular figure 474 of this slide deck, we see a wing of finite span, which is indeed thin, as we assumed earlier. And we'll also say that the wake itself behind the airfoil is three-dimensional. The region of influence we'll color in as two-dimensional on the wing surface. These shaded crossed hatches represent the two-dimensional flow. Everywhere else in the flow might be considered three-dimensional because it's having other effects. Notice that a disturbance at B has a right running wave, which is a Mach line, which we just find in the first part of this class, and A has a left running wave, which is another Mach line. Everything bounded and disturbed along the surface has a region influence downstream, which is bounded, and therefore could be considered a two-dimensional flow, which exists between, say, 2 points A and B. Now let's say we take this previous figure and cut the wing at BD and AC, here and here. Then we might have a figure like this. This is the so-called unswept wing. And this line is really supposed to be in the vertical direction of the page, but the scan is skewed, excuse me. And of course, we call that the ends are unraked. The flow over the entire planform is now entirely two-dimensional in this type of wing if it could indeed be developed. You might see now the motivation of designing an aircraft like the X-29. Now, the flow over the entire planform is indeed entirely two-dimensional according to the assumptions we just made. Indeed, the angles of the wing where it's clipped, if you will, are larger than, of course, the Mach lines, which are created at the disturbances at, say, points A and B at the tips of the wing. Now, an unswept wing with ends within the Mach cone, which are defined as, say, alpha from some disturbances on the wing, will have entirely two-dimensional flow except at the tips of the wing. And so we can solve for this particular flow with our developed theory. Finally, we might examine another wing. What if we have a wing which is swept back? And so here's the leading edge of the wing, and it sweeps back with the flow. A forward swept wing would have a line going, of course, in the forward direction relative to the fuselage. A swept back wing sweeps back the wing in the direction of the flow at some acute angle relative to the downstream direction. So that's a swept wing. In this case, from the disturbances created at the wingtip and at the center line of the fuselage, the flow will appear entirely two-dimensional on the wing. But this will appear entirely two-dimensional to an observer moving along the span at such a speed that the observer's coordinate system in the oncoming flow is normal to the span-wise direction. And that's a key statement. The observer will be moving along the span at a speed in which the observer's coordinate system in oncoming flow is normal to the span-wise direction. Take a few seconds and consider this all-important statement. Now, if we sweep the wings back even more and make the same diagram, we might say that the leading edges are behind the Mach lines from the forward point, and therefore no part of the flow would be indeed two-dimensional in terms of the flow. It does not conform to our two-dimensional MOC theory. Think about this, where these dashed dot lines are indeed the Mach angles, which create Mach lines from these disturbances. And you can see the sweepback angle of the wing is smaller than the local Mach angle at its location of creation, at the wing tip and at the root and forward part of the fuselage. Now, remember that the disturbances will always originate in the flow and propagate in the region of influence of the particular Mach cones. And so wherever we're changing the angle of a wing, in this theory, we might view that Mach lines appear. We draw the Mach lines in the left and right running directions respectively, left running, right running, and crosshatch areas which would be considered two-dimensional flow. We might be able to analyze those particular areas with the presently developed theories, which we discussed in previous classes. Let's make some particular notes about the so-called supersonic and subsonic leading and trailing edges. We'll consider a swept wing a finite span. That means it's not infinitely long in span, of course. It has a finite span just like a real aircraft, and the wings are swept back. We will resolve the free stream velocity into components of, say, u sub infinity. So u sub infinity is indeed our free stream velocity, and we want to decompose it into particular components which are normal and tangential to the flow. Now, a fluid parcel, that is a little fluid element, which might move in the spanwise direction, that is, in the cross-stream direction of flow along the wing, with uniform speed u sub infinity, n is, of course, now meaning spanwise direction, will observe a two-dimensional flow with free stream velocity u infinity past an unswept wing. Let's say that again. A fluid parcel moving with the span with uniform speed u sub infinity will observe a two-dimensional flow with free stream velocity u sub infinity n past an unswept wing. So we're comparing u sub infinity n between the swept and unswept wings. Now remember, in this case, c sub infinity will go as u infinity times sine of alpha sub infinity. Here alpha is the free stream Mach number, which of course is defined only as Mach number and alpha. Mu will define mu as the sweep angle of the wing relative to the downstream direction. So alpha is the free stream Mach angle and mu is the sweep angle. Now, u infinity of n will equal u infinity sine mu through trigonometry. And we can write the following important result through the trigonometry. We can write m sub infinity n equals u infinity n divided by the ambient speed of sound. And through our substitutions of c infinity equals u infinity sine alpha infinity and u infinity n equals u infinity sine mu, we can write m infinity n equals sine mu over sine c infinity. This will indeed give us the equivalent two-dimensional flow if it's supersonic if mu exceeds the Mach angle. That is, it will be subsonic if mu is less than, of course, infinity. For example, we might state that the leading edge is supersonic while the other flow is subsonic. But of course, in the global system, it's always supersonic over the wing. But the normal m sub infinity will be subsonic. This is an incredible idea and is counterintuitive. We'll try and understand this through a little bit of math and some examples. But write down these equations I mentioned and you'll see for yourself through the trigonometric outline of the wing, as shown in figure 478 of slide 1197 of the slide deck. Let's now write down some of these trigonometry identities. Here, in part A on the left, we'll see a so-called supersonic leading edge. And on B, we'll observe the so-called subsonic leading edge, even though both cases have supersonic incoming flow. That is, the Mach number in the normal direction, that is in this case not the normal direction relative to the wing front, but along the spanwise direction will give us a subsonic Mach number, according to the equation m infinity of sine mu over sine c infinity. You can see this here on the right, where we have an increased swept wing, and therefore, according to these equations and trigonomic identity, we indeed find that mu is less than A sub alpha. Now, this notation is absolutely significant due to how lift is generated on the wings. Let's try and illustrate this basic concept through a flat plate case. Let's say that the pressure at the trailing edge of the airfoil is equal. That is, the pressure on the top and bottom of the trailing edge of our airfoil is equal. And we have a very, very thin airfoil, which we're approximating as, of course, a flat plate. Now, the circulation theory will be determined. That is, the circulation will be determined by the theory and, of course, the use of the Kutta-Joukowski condition, which you learned in basic aerodynamics. In the supersonic flow, we'll see that lift distribution is constant over the chord in the context of the simplified theory. So we'll say that the lift distribution is relatively constant, which is a good assumption for these very, very thin airfoils. This indeed will lead to the following three major points. The first is that supersonic leading and trailing edges will have finite lift loading, which should be obvious and is connected to nature. A subsonic leading edge will tend to have a very high lift loading and a negative drag force in this case, which is very counterintuitive in the supersonic flows. Therefore, a sharp subsonic trailing edge will have zero lift loading. Let's illustrate these points from what I just mentioned in the following figure in 481 of the slide deck. Here we see a chord-wise distribution of static pressure on a flat plate at non-zero angle of attack alpha, in the subsonic case on the upper left and the supersonic case on the upper right. Here's the supersonic case and here's the subsonic case relative to m infinity. This is the normal force distribution on the plate. According to the assumptions we laid out and the earlier assumptions in this class. Now, in supersonic flow, we can try and use the idea of superposition if we can make these assumptions. So we might be able to use perturbation theory of aerodynamics, and then we can superimpose particular solutions and combine them with, of course, the swept wing theory. We can add the effects in independently, so it's really a linear theory, due to incident angle, the thickness of the airfoil, the camber, and find the so-called perturbation pressure distribution on each part of the composite profile. Portions of the boundary which have a subsonic leading edge should have a rounded nose to avoid a large drag, which we can account for later. The supersonic leading edges should always have a sharp edge to avoid large pressure drags due to, of course, detached shocks. And so in a low speed or moderate speed supersonic vehicle, it's important to have sharp edges, unlike the subsonic case. Now we can illustrate this through a particular figure. Say we have figure 483. And we have points AB, DE, BC, and CD, which all make particular lines. So the curve from A to B is the supersonic leading edge, and the flow near that leading edge will be supersonic normal to the wing of finite span. We'll also have line DE, which is a supersonic trailing edge, obviously for the same reasons as curve AB exists up here in the figure. Now, B to C and C to D will have a subsonic leading edge as the velocity component is normal to the edge is less than C. The same can be said about C to D. And therefore, the disturbances in the flow, in the supersonic flow, will propagate along points C to D and cover the plane form of the wing. And therefore, the flow can be adjusted to satisfy the Kutta-Joukowski condition. So let's make some notes about the so-called swept-backed wings now. Sweep angle will be defined as angle capital A with an angle of attack of the wing of alpha, and we'll resolve m infinity into three major components now. And so we're extending our previous two-dimensional theory to include angle of attack. We'll decompose m infinity into three major components. The first is on the plane of the wing and normal to the edge of the wing. The second is normal to the plane of the wing. And the third is in the plane of the wing and tangential to the leading edge. So we've added a third decomposition component relative to the original decomposition which we talked about earlier in this class. Let's illustrate these concepts through figure 484 of the slide deck. On the left, we have a figure of a swept-back wing. Its real chord is L. Its chord in, of course, the normal direction relative to the leading edge is L cosine A. We also have points A to A and B to B. The sweep angle, defined as from a non-swept wing, is capital A, once again. The incoming Mach number is m infinity. The Mach number normal to the wing leading edge is m infinity cosine a cosine alpha little a. And of course, the tangential direction is m infinity sine a cosine a. So this is just from trigonometry. We have the sweep angle, capital A, can also be from the original flow direction to the shortest direction across the wing, B to B. Now, over on the right, we can decompose this wing section. Let's just say it's a basic diamond airfoil, which is swept. It has, of course, a length in chord L, which is the original one, and L cosine A, which is the sweep angle, which is long here on the left, L cosine A, and it has a thickness T. Then we can break down the flow directions with respect to the angle of attack alpha, which is written as A here, and A sub E relative to the shorter section. So this section here is right here, and the upper right section is in the streamwise direction L. And you can therefore see there's a modified Mach number along the direction of L versus L cosine lambda. And that's written, of course, as m cosine alpha and m cosine A cosine alpha, which is the angle of attack. We can now introduce a subscript E, which we showed in the previous slide, and that will denote the flow quantity as observed by moving in the observer direction along the wing. Using this previous figure, we can then write through trigonometry m sub infinity E, which denotes the flow quantities observed by the moving observer, as m infinity sine A, which is the angle of attack squared, plus m infinity cosine A cosine capital A squared square root. Try that out from trigonomic identity. And you can see, indeed, this is equal to m infinity square root 1 minus sine squared A cosine squared A. We can then solve for A sub E, that is the angle of attack observed by the observer. This indeed will be A sub E of inverse tan of tan A over cosine capital A. Now, we can define delta as the thickness ratio of the plane parallel to u infinity as L over T, or L cosine A over T for the sub E direction. And we can write and relate the thickness ratios between these two directions of the airfoil with respect to the sweep angle capital A. That'll be delta sub E as T over L cosine A equals delta over cosine A. Now you'll see that indeed the lift is not changed by an observer's motion. It's going to be what it is because of course it's from the wing. And we can write the lift in two particular ways from the figure, where L of course is the lift force, and it's non-dimensionalized by gamma p infinity m infinity squared times L times B over 2. So the denominator is for the normalization. We can then replace terms in the denominator to find the lift CLE also across these particular spans. Here's the E direction where my cursor is moving, and L is the streamwise direction. We can independently write CLE in the same way, but replacing, of course, L versus K should be a gamma. This is a typo. Now, of course, the lift does not change, so we can set CL equal to CE, and we can, of course, make these substitutions, eliminate, and we find the following equation. We can find, indeed, that CL equals CE, and therefore m infinity E over m infinity squared equals CLE times 1 minus sine squared A cosine squared A, where A is the sweep angle and little a is the angle of attack. Now, if we neglect the tangential velocity influence on the drag, which is relatively small compared to the stringwise one, we can write the drag coefficients in the same way. And naturally, the drag coefficients, like the lift coefficients, should also be equal. This is what we've done in 757 and 758 from trigonometry and the normalization in figure 484. I'll let you try that one out yourself. We then set CD equals CDE, and now we can find, indeed, that CDE cosine A m infinity sub E squared over m infinity goes as CDE cosine A, sweep angle, times 1 minus sine squared A cosine squared little a, which of course is the angle of attack. Now we have concisely found from geometry only the equations that take the relationships for angle of attack for a swept wing. And therefore we can find the values of ME, the angle of attack, and the thickness ratio of the normal direction across the swept wing from only the properties of the incoming flow, which is amazing. And we'll see now that the drag force can be found by adding a skin friction coefficient, of course, to account for the turbulent shear stress on the face of the wing. And so we might write CD total equals CD plus CF, and so CF is like a correction factor. Now, when the angle of attack is small, we might say that A goes as, say, epsilon, a very, very small angle of attack. Then we can use the small angle approximations, just like Boostman did. He wrote cosine of A goes as 1, and tangent of A goes as A, and arctangent of AE goes as AE. So this is your typical small angle assumption in trigonometry. We're saying the angle of attack is very small, a few degrees. We can then write from our previous equations upon making the substitution that m infinity E goes as m infinity cosine A, and AE goes as A cosine over the sweep angle. We can then substitute these relations into our previous formulas for CL and CD, and we can write CL goes to CL cosine square of the angle of attack, the sweep angle, and the drag total goes as the drag coefficient times cosine squared A plus the skin friction from this equation up here. And so these are amazing equations. You can see indeed that the lift and drag will be going as the original value of cosine squared A and cosine squared A plus CF respectively. We can further say that the thickness is small, which is very reasonable for an airfoil. And the angle of attack is small, and then linear theory will yield the two following equations for CL and CD, which we've used these assumptions and applied previously. Now let's look at these equations carefully. We can see that the first term here in the coefficient of drag is induced drag to lift. And you can see its relation because, of course, for A cosine A over square root of m infinity squared cosine squared A minus 1 is the same as the first term in the coefficient lift equation. And so indeed the coefficient of drag should be related to the coefficient of lift with an extra angle of attack term squared. The second term, of course, is due to what we call the wave drag, and that's, of course, due to the thickness of the airfoil. And you can see this here with, of course, the thickness ratio term delta sub E squared along the normal direction of the flow, tangential direction relative to the wing leading edge, plus the skin friction parameter. Now let's find the derivative of CL with respect to alpha and make a plot. Here, this is from Ivy and Bowen of the NACA from their original report. On the x-axis is the sweep angle. On the y-axis is the slope of the lift curve, DCL with angle of attack. So that's the derivative of the lift coefficient, equation 762, with respect to angle of attack A. Now, you can see at Mach 1.5, we will have this particular curve. For double wedge wings, which we just looked at, we might have an angle of attack with thickness ratio of 0.05, and at Mach 2, if we increase the sweep angle, we get lift benefits. And at Mach 4 and 8, we have relatively flat lines. So you can see at low supersonic Mach numbers, say between Mach 1, 1.1, 1.5, 2, maybe even 3, as we increase the sweep of the wing, which is capital A in degrees, to say higher and higher values, we'll get higher and higher values of DCL over alpha, which is amazing and is, of course, the theoretical proof through these assumptions that if we follow, we'll have lift benefits through, of course, sweeping our wings. And this is the whole reason that we sweep wings in practice and theory. So you can see the Sweptback yields substantial improvements in the performance of the wings. Let's now turn our attention to the similarity theory of supersonic wings, just like we developed for transonic and hypersonic flow. We'll derive a particular rule by which the flow pattern around anything wing at small incidence in a supersonic flow is related to the flow past an finely related wing at m infinity of 2 to the half power. For supersonic flows with only small perturbations from the uniform flow in the x direction, we'll see that the velocity potential perturbation goes as particular equation 764, which we're not deriving in this class. So it is indeed, we talked about this equation previously in the hypersonics module, but it is an equation for the velocity potential in 3 dimensions in small perturbations about the x direction. Here we'll introduce a parameter beta, which is a non-dimensional parameter which we call the off-design parameter. We'll write beta equals the square root of m infinity squared minus 1. And now we define, of course, m infinity as being 1 or larger. We can now introduce transform coordinates, and we'll let x prime equals x, y prime equals beta y, z prime equals beta z, and phi prime of the arguments go as beta squared phi. And so we are now working in transform coordinates. Our transform equation through this careful choice is now negative partial 2 phi prime partial prime x squared plus partial 2 phi prime partial y prime squared plus partial 2 phi prime partial z prime squared. Look at this equation carefully. It is very much clear that the original equation can be transformed into this equation, and they're exactly the same if you let m infinity equals the square root of 2, as in the off-design parameter here in equation 764. So therefore, we can conclude that the factor beta corresponds to dimensions of the lateral dimensions of the body that are larger than the original body. That is, it's a closed similarity theory for m infinity, of course, equals 2 to the half power, square root of 2. Now the linearized pressure coefficient, therefore, if we can solve that equation or find it in a wind tunnel and transform it to a flight at corresponding points in two flows, are infinitely related as c prime equals beta squared c sub p. Now c sub p is the pressure coefficient in m infinity of 2 to the half, the square root of 2, whose body lateral dimensions are beta times larger, that is 1.414 times larger than the corresponding lateral dimensions of the body, corresponding to the pressure coefficient at 2 to the half. So you can see the simple logical argument leads to the similarity theory of supersonic wings. It's so simple and straightforward. Now, let's summarize this particular rule in words, which is written from an NACA report. It's read, the pressure coefficient at any given point for a flow at m past a given wing is greater by a factor of the inverse of beta than the pressure coefficient at corresponding for a flow at Mach square root of 2 past a wing which is alike in all respects except that its aspect ratio is greater by a factor of beta than the original wing. And this little similarity rule gives us the ability to test supersonic wings in wind tunnels and scale them to flight. There are no identical rules, which we won't present here, for the coefficient of drag. All variables will form in a combination of beta times the aspect ratio. As you can see at this point in this class, we have unique similarity rules for supersonics, hypersonics, and transonics. Let's now take a few seconds to look at the particular drag of thin wings having straight leading edges and trailing edges in the same dimensionless profiles in all chord life planes from the publication of Lorentz from NACA. You'll see on the x-axis we have placed AR times the square root of m infinity squared minus 1 on each x-axis. This is nothing but the aspect ratio times beta for the swept wings, which we discovered and discussed in this class. On the y-axis, we have coefficient of drag divided by the aspect ratio times the thickness ratio squared. And so the y-axis is non-dimensional drag, and the x-axis is aspect ratio times beta, which is the non-dimensional coefficient we just discussed with our transformation. You can see particular curves for two-dimensional unswept wings up here, and various sweep angles of wings for double wedges with different shapes of where the diamond is placed, indicated by the line in the upper right corner of each figure. Let's trace across lines at different particular Mach numbers. You can see indeed with varying aspect ratio and beta parameter how the drag increases and falls off almost at an asymptotic line, which can be drawn through each of the particular curves. In this class, we looked at regions of two-dimensional flow based on our Mach angle theory, which we introduced at the beginning of the class. We then looked at supersonic and subsonic leading and trailing edges and made a few assumptions. We derived through the exact same work as Adolf Busemann the theory of swept wings and showed that indeed we get a CL alpha advantage for sweeping the wings at different Mach numbers, especially just above the transonic condition. This is why we see this almost free lift, if you will, being generated as we sweep the wings. And in fact, it also reduces the transonic drag or speed of sound barrier. You'll note that the Bell X-1 did not have swept wings. It was really only a transonic aircraft. To truly go supersonic and break the sound barrier, if you will, we had to sweep our wings, and aircraft just after the Bell X-1 were all swept. Indeed, the sweep wing theory was also known by the Soviet Union independently of the Americans. We also look at similarity theory for supersonic wings, and we apply this as the aspect ratio times beta through an argument of the perturbation equation of compressible three-dimensional flow and supersonic flow about the parameter square root of m infinity squared minus 1. Thank you very much for your time today. I'm Professor Steve Miller.